Okay, we are going to learn about theoretical probability today. Okay, so first we'll start with our definitions. Theoretical probability. It's the probability based on analysis of all possible outcomes, not just our experiment, also called classical probability. Okay, a sample space is a collection of all possible outcomes, also called a sample set. So for example, a coin toss. Whoops, sorry for that writing. A coin toss, heads and tails, are all possible outcomes. A die, all possible outcomes is 1, 2, 3, 4, 5, and 6. And an event here is the set of outcomes that have a common characteristic. Okay, a set of outcomes that have a common characteristic based on how we define it. All right, so here is theoretical probability, the formula. So write this down. PA is a probability that event A can occur. Okay, and NA is the number of ways an event can occur, the number of ways it can occur. And NS is a total number of possible outcomes in a sample space. Okay, so write that down. Now, let's say I have 2 dice to illustrate the example. What are the possible outcomes of 2 dice being thrown? So some of you might think, well, you can't get 1 because you have 2 dice. So you can have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? So you might think that these are the possible outcomes, 11 possibilities. But in fact, I wrote them down. There are a number of ways that 2 can occur. How many ways? These are events. The event is that 2 occurs, 3 occurs. So these are the events that can occur, but they can occur in a number of ways. So this is the number of ways 2 can occur. Okay? Basically 1 and 1. But 3 can occur by the first dice being 2 and the second dice being 1, or it can be the first dice being 1 and the second dice being 2. Same thing with 4. We can have the first dice 1 and the second dice 3, or we can have the first dice 3 and the second dice 1, and of course 4 can occur with double 2s. And the same goes for 5. We can have 1 and 4, 4 and 1, 2 and 3, and 3 and 2. 6 can occur in 1, 2, 3, 4, 5 ways. 7 can occur in 6 ways. And of course, 8 can occur in 5 ways, etc., etc., etc. If you want to go over them, you can pause it and take a look. Okay, what is a total number of possible outcomes? Was it 11? No, it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, and 36. So we counted them out individually, all the outcomes. Later in the future, we will learn ways to calculate without counting, but bigger results. So NS, which is the total sample space size, is 36. So what is a total number of possible outcomes? Well, you say NS equals 36. What is the sum? What sum or sums have the greatest theoretical probability? Well, 7 has the greatest theoretical probability. So they're not all equal. 7 can occur in the most ways, so it has the greatest theoretical probability. What is that probability? Well, the number of ways 7 can occur, if A is 7 occurring, then that can occur in 1, 2, 3, 4, 5, 6 ways. So NA over NS is 36 over 1 over, sorry, NA over NS is 6 over 36, which is equal to 1 over 6. We just simplified, right? 6 over 36, divide by 6, I get 6, divide by 6, I get 1 over 36. What sum or sums have the lowest theoretical probability? Well, this does. 2 and 12. Okay, 2 and 12 have the lowest theoretical probability. What is that probability? Well, how many ways? Which, if we're having the probability that I get 2 or 12, well, that's 2 plus, sorry, that's 1 and 2. So these are the sums. So we're talking about what's the probability of getting 2 or 12? Well, the number of ways it can occur is 2. So NA over NS is 2 over 36. We got that from there. And when we simplify, you divide 36 by 2, you get 18. You divide that by 2, you get 1. And that's how we got 1 over 18. Okay. What is the probability of rolling a 9 or greater? So how many ways can I roll 9 or greater? Well, I can roll it in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ways. So these are the ways that I can roll 9 or greater. So NA, now I can say let A represent rolling 9 or greater. In which case, N of A is 10. Oops. Whoops. Let's erase some things. Okay. So then P of A is equal to N of A over N of S. Well, N of S we already know is, well, that's equal to 4 plus 3 plus 2 plus 1, which is how we got 10 in the first place, right? And N of S is 36, so our answer is 5 over 18. And whatever that turns out into percentage, we could always work that out. Okay? Now, there's something called set notation. So S is essentially, we're just defining it as 1, 1, 1, 2, 2, 1, 1, 3, basically all our different combinations, okay? And the event, if A is the event of rolling 11 or greater, how do we mark that in set notation? Well, we can say, well, 11 is represented by 6, 5, 5, 6, and 6, 6. So, how we choose to represent the event should make some kind of intuitive sense. So we're going to use a tree diagram. We're going to learn about tree diagrams now. And we're going to use tree diagrams to count. So here, Fiona has 2 shirts and 3 pairs of pants that she can wear. If she randomly chooses her outfit, what is her sample space? Assuming she picks a shirt and a pants. Okay, so what is her sample space? So we have to define a sample space with set notation somehow. Okay? Or, sorry, we're using a tree diagram. So we start from S. Now she can pick, for shirts, she can pick either a red or a blue shirt. And if she picks a red or a blue shirt, she can pick green, white, or orange pans. So green, white, or orange. So red goes with green, white, and orange, or blue goes with green, white, and orange. Now you notice if she picks green pants, she can do that in two ways, red and green or blue and green. Anyway, so our set notation is red, green, red, white, red, orange, red, green, red, white. Let's erase some things. So we can go red, green, red, white, red, orange, blue, green, blue, white, or blue, orange. Okay, so that's our set notation there. So it makes some. What is the probability she chooses an outfit she hates? Fiona hates wearing blue and green together. She also hates wearing orange and red together. So Fiona hates wearing blue and green. So blue and green. She also hates wearing orange and red. So she hates wearing orange and red. So what's NS, by the way? So we're talking about probability now. So we're going to have to say, let A represent Fiona. Actually, Fiona, if A equals, what is it? Red, orange, or blue, green. Let's write this nicely. Okay, so NS is equal to 1, 2, 3, 4, 5, 6. How big is S? 6. And NA is equal to 2. Okay, so we already did that over here. Clear pen markings. So these are what we hate. So we have our, we called it C. Actually, I called it C in this example for some reason. So N of C is 2. N of S is 6. So probability of C is NC over NS. We have all our numbers. We have 2 for NC and 6 for NS. So the probability of choosing something she hates is 1 over 3. So here's another definition. Complement. Set of possible outcomes not included in an event. If outcome is denoted A, then the complement of A is A prime. Okay? So the probability of A occurring and the probability of it not occurring is always going to be 100%. Okay? Because something's either occurring or not. It covers all possible scenarios. So if it's not occurring or occurring, the probability of that is 1, which is 100%. And by definition, you know, if that's true, then I can subtract 1 minus P A prime, the complement of the probability of the complement of A. If I subtract it from 1, I can get PA. Okay, this comes in handy. Write all of these formulas down, but this one's enough. These two are derived from that. Okay, so we're gonna do an example of complement. Battleship is a 10 by 10 grid game where you shoot at a grid and attempt to hit a ship. What is the probability of hitting a ship on your first shot? What is the probability of missing a ship on your first shot? So what is the probability of hitting a ship on the first shot? So there's 10 by 10. Let A represent the event of hitting a ship. So the probability of hitting a ship is, well, that's 2 right there, right? That's 3. That's 3. That's where we get the 3 from. That's 4. And that's 5. So these are the number of ways you can hit a ship. So there's 100. Oh, sorry. And there are 100. That's from 10 by 10. There's 100 little dots here. Okay? So the probability of hitting a ship on your first shot is NA over NS. Now 2 plus 3 plus 3 plus 4 plus 5 turns out to be 17. And S is 100. So the probability of hitting the ship on your first shot is 17. Therefore, the probability of hitting a ship is 17%. So then what's the probability of missing the ship? Well, we could count 1, 2, 3, 4, 5, 6, 7. But if I let A prime represent the event of missing a ship, then the probability of missing is just 1 minus the probability of hitting, which is 1 minus 0.17, which is 83. So therefore, the probability of missing the ship is 83%. So now this is for you to try out. A box contains 3 bran, 4 banana, 5 blueberry, and 3 carrot muffins. What is the theoretical probability that you will not randomly choose a blueberry muffin? Not. So think about that. Well, I could calculate the probability that I choose one of these muffins, or I could, and not the blueberry muffin, or I could, or I could, oh, for God's sakes, or I could calculate the probability of selecting a blueberry muffin and then doing 1 minus the blueberry muffin. You try it out yourself. Finally, we have the definition of odds. We have odds in favor, which is just equal to the probability of something occurring to the probability that it doesn't occur. Okay? Ratio of the probability that an event will happen to the probability that it will not. Odds in favor of A, PA to P of not A. And then we say odds against. It's basically just these two switched. Probability that it occurs to the probability that it doesn't occur to the probability that occurs. This is something that you're just going to have to remember. Okay? And we'll have plenty of practice with that. All right, so let's end that video for now.